going to be talking about applications of derivatives. In the book, this is chapter 4. And we're pretty much going to follow the book in this chapter in terms of progression of the content, pretty much very, very closely to your author. Before we begin with the calculus, we're just going to talk about some basic terminology, and then I'll tell you why we need to talk about this type of terminology. So, ultimately, these are the kinds of questions we'd like to answer. What shape of a can minimizes manufacturing costs? Okay. And a question like, what dimensions of a box with fixed surface area maximizes volume? Okay, and the types of applications are endless to the calculus that we're going to study in this chapter. So in both of these questions, we're looking for the optimal answer. Okay? And of course, every good optimal answer has to take into account its constraints. And those are the physical constraints that we're working with depending on the problem. So here, in both of these, what we're looking for is the optimal or best way of doing something. What's the best way of doing something? And in asking those questions, what usually boils down to is, what is the maximum of some quantity? What is the minimum of some quantity? So in other words, if I want to find the shape that minimizes the manufacturing costs, I could try to model the manufacturing cost as a function and try to find the minimum of that function. If I want to find the dimensions of a box that maximizes volume, then I might find a function that models the volume and maximize that function. So a lot of these optimization problems really boil down to a function and finding the maximum or minimum of that function. So that's where we're going to start. So let's take a general function, g of x, whose graph appears here. And let's try to classify some of the interesting points of this graph. Well, the notion of maximum is basically the highest point on the graph. So in this case, the maximum occurs here. Okay? So we're going to call that the absolute maximum. Some books call it the global maximum. Okay? And the lowest point on the graph, which is this one, represents the absolute minimum, or global minimum. Okay? And trying to find the absolute maximum, absolute minimum is not as straightforward if we don't have the graph of the function. So we're going to come up with some tools to help us do that. So now that we've seen what it looks like on the picture, we can write a little definition that's more accurate as to what it means to be an absolute maximum or an absolute minimum. And the definition isn't far from our intuitive understanding of this. So here's the definition. F of A is absolute maximum of a function of f if f of a is larger or equal to every other function value. Does that make sense? So f of a is an absolute maximum if the value of the function at a is larger than the function value at any other point, okay, within its domain, of course. So similarly, how would we define the absolute minimum? We say f of b is the absolute minimum if f of b is smaller than or equal to every other function value within the domain of f. Okay? So that's a mathematical definition of ideas that I just outlined here in this picture. We could get some examples of that right now. Because if we take simple functions, then we know what they look like graphically. So we could set some standard on how we want to represent our absolute maxes and mins. So if we consider the function y equals x squared, okay, the graph of that is a parabola, concave up, with its vertex at the origin. Okay, and if I don't specify the domain of a function, then we're going to assume the largest domain possible. So according to our diagram here, where is the absolute minimum? 0, 0. 0, 0. Okay, so that's the absolute minimum. Okay, and what is the absolute maximum? There is no absolute maximum. Okay? Because any value you pick, you can always get a larger value because the graph goes up to infinity in both directions. So we don't always have an absolute max and an absolute min. As a matter of fact, we could draw another picture over here. And according to this diagram, do we have an absolute minimum? No. Well, it would be here, but this isn't part of our function. So in this case, there are no absolute extrema. So the word extrema really combines the two ideas of maximum or minimum. There are no absolute extrema here in this picture. So our overall goal, like I said in the beginning, is to find what these maxima and minima are. But you could foresee a problem because sometimes we may not have a max or a min or a both in a function. So let me give you some other examples where you cannot find an absolute max or absolute min. Does this function have an absolute max? So if I call this A, B, and C, where's the absolute max? B. At B. Okay? So that's the absolute max. And the absolute min? Is it at C? No, absolute max. No absolute min. Somebody said limit, but our definition of absolute min does not involve a limit. It involves the function value at that point. Okay? So it looks like C would have been a candidate except the function is not defined at C. Okay? So we want some criteria before I can tell you how to find the maximum or minimum. We want some criteria that will guarantee that we have one. Because it's not always the case that we have an absolute max or an absolute min. And there's a theorem that tells us what the criteria need to be for us to know that we definitely do have both extremas. And this is called the extreme value theorem. I'll refer to it as EVT. Okay, extreme value theorem. It's very intuitive. Once I write it, you'll see why. So here's what it says. If f of x is continuous, on the closed interval AB, then f assumes an absolute max and an absolute min. Okay? So there is a value within AB at which point you have a maximum and another value between A and B at which point you have the lowest value. Okay? And what's the criteria? The criteria is you need to be, the function needs to be continuous. Okay, but that's not it. Because if that was only true, we'd have a problem. You go to this function over here, y equals x squared. This is a continuous function, right? Okay, but that's not enough. The other condition is that this continuity should be true if we're working on a closed interval. Okay? Then we'll be guaranteed an absolute max and an absolute min within that interval. So to demonstrate, let's take the same function, y equals x squared. Well, not really the same function, but let's take the same function with a different domain now. Now I'm specifying what the domain is. X is between -1 and 2. So that's the closed interval that I want. Okay? And according to the theorem, we definitely will have an absolute max or an absolute min. I mean, and an absolute min, not both. So of course, if I draw this function, so it looks something like this. Okay? This is the graph of y equals x squared in that closed interval. And so you see, where's the absolute max here?
2.4.
At 2. At 2. So, let me write a sentence that will help you identify this without being confused whether to say 4 or 2. 4 is the absolute maximum value occurring at x equals 2. Okay? So if you're asked to say where is the absolute value, the absolute maximum, you say it's at x equals to 2. Okay? What is the absolute maximum value? The absolute maximum value is at 4. Okay? That's the maximum value. And this is where it occurs. Okay, so that's the distinction between the two parts of that sentence. And so similarly, we would say that 0 is the maximum or the minimum value occurring at x is equal to 0, occurring at that location, which is here. That's the absolute minimum. This was absolute max. Okay? And some of these other pictures, like this one over here, and this one over here, tell us that, show us that we really need these conditions. That they be continuous on a closed interval. Right? So although this is continuous, throughout the interval AB, it doesn't have an absolute extrema. Why does this not invalidate the theorem? It's not closed. Why is it not closed? Right, because A and B are not included in the interval, right? All right. And here, although we're working within a closed interval, right? There is a point in there at which the function is not continuous, right? Okay. But in all of these examples, it was very easy to see what the absolute maximum is. But this theorem, although very powerful, doesn't tell us how to find it. Just tell us that it exists.
Does the point -1, constitute a local maximum?
No. I want to talk about local maxima now, and that idea only makes sense within the inner. The endpoints don't qualify. Okay? So as I was saying, this extreme value theorem is an existence theorem. It just tells us that absolute maxes and absolute mins exist. It doesn't give us a way of finding it. Okay? By the way, the proof of this theorem is very difficult, and it's well beyond the scope of this course. So I can talk about it if you'd like outside of the class, but it requires some mathematics beyond calculus. Okay? But we'll prove some of the other simpler theorems later. But to start, this theorem doesn't tell us anything if the function is not continuous. In other words, if we consider this example over here, okay. Here, consider this function here. What can you say about the absolute max and the absolute min of this function? Do they exist?
No.
Well, you want to take the highest point in the function. Is there such a point?
Yes.
There is, right here. That's the highest point. There is no other point higher than it, right? And so that's the absolute max. And there is an absolute min as well. That's the lowest point in the graph. Okay? But the theorem doesn't tell us anything about these types of functions. In other words, we may have an absolute max and an absolute min, even if the function is not continuous, but we can't use the theorem to guarantee that. We have to treat those functions on a case-by-case basis. Is that clear? So, this isn't saying that we're going to have absolute extrema only when it's continuous on a closed interval. Okay? We may have absolute extrema despite that. But we have to treat those functions on a case-by-case basis. Okay. So, I'm going to go back to the first picture we drew to talk about different types of maximas and minimas. So, go back to a picture similar to what I started with. Okay. We identified the absolute max and min of this graph, G. But then there are other interesting points on this graph, namely the peaks and valleys of this graph. And we can identify the peaks and valleys very quickly. What are the peaks here? Where do they occur? At B and D, right? Those are the peaks. And the valleys? C and E, right? These are the valleys. Okay. Now A and B, or I'm sorry, A and F don't qualify as peaks or valleys. They're called the endpoints. Okay? So when I talk about peaks or valleys, I'm only talking about within A and B, within A and F. Okay. So how can we create a mathematical definition around the idea of a peak? This is a peak right here. Yes? So we want to write down a definition. We want to write down a description of this that's accurate mathematically and simple at the same time. So how could you describe a peak?
Maximum.
It's a maximum, right? But only if you're looking locally, right? So if you look at the big picture, that's not the maximum is here. But if you're only concerned with the function near that point, okay, then you can say that you have a peak if that value is the largest value if you're close to that point. Okay, if you're looking at it locally. All right? And similarly, this is a valley because locally that's the lowest value. So let's write a definition that says all that. Okay? And we don't call them peaks or valleys, we call them local maximum and local minimum. So here's a definition. So f of a is a local maximum of f if it's the largest value, so that f of a is more than or equal to every other function value for x near a. Okay? F of a is the largest value, okay, among all the values of x, as long as you're just talking about those values of x that are near a. Okay? So, and we can make this a little more formal, but I think you get the point. The way to say this formally is to say that f of a is a local maximum if there's an interval containing a, okay, so that within that interval, f of a is the largest value. Okay, so for us, here g of b is a local maximum, and this is the interval we can consider right here. Okay, for values of x within that interval, that point is the highest point in the graph. And the local minimum is defined very similarly. So if we say that f of b is a local minimum, f, if f of b is smaller than every other function value of x, for values of x near b. Okay? So for example, this would be a local minimum because we could find an interval around e so that within that interval, that point is the lowest point on the graph. Okay? The term that combines the ideas of local max and local min is local extrema. Okay, this gets us one step closer to trying to find out what the absolute extrema are. And here's the plan. See, according to this picture, your absolute maximum is either going to be within the interval or at an endpoint. Does that make sense? Okay. Now, if it's at an endpoint, it's at an endpoint. That's fine. But if it's within the interval, then your absolute maximum should be one of your local maximum values, right? So you can't have an absolute maximum that's not a peak. So for example, here's a local max, here's a local max. One of these will be the local max if it's not at the endpoints, right? So where do we look for absolute maxes? We either look at the endpoints, okay, or if it's within the interval, we're looking at the peak, a local max. Same thing with absolute minimum. It's either going to be at the endpoints or at one of the valleys, one of the local mins. So here's our strategy for finding absolute extrema. Okay? We're gonna we know that they're either going to be at the endpoints or one of the local extremes. Okay? The first test is not very difficult to do. We can just evaluate the function at the endpoints. Okay? And if we know that it's going to be on the endpoints, then we take the largest value, either the left endpoint or the right endpoint. But if it so happens that the absolute maximum or absolute minimum is not at the endpoints, then we have a more complicated situation, because we have to look within the interval, and there's a lot of numbers within the interval. But at least we have simplified our approach, because the only candidates are the local extrema. Now, if the function is not differentiable anywhere, then it looks too weird to study, so we're not going to worry about that. So some of the assumptions that we're going to make, the function should be differentiable at most places in the interval. So that's how we can use the tools of calculus to simplify our work, make it more efficient. Here's another theorem. This theorem is of fundamental importance, and it's more practical than the other theorem, the extreme value theorem, because this actually gives us some clues as to where to look. Fermat's theorem, Fermat made an observation about the qualities that local maxes and local mins have. Okay? And we could probably come up with intuitively what the theorem says, but I'll just write it down. F of A, if f of A, let's say f of C is a local extrema, local extreme value, then either f prime of C equals 0, or f prime of C does not exist. Okay? Now if we keep looking at this picture now, we're going to see that that kind of makes sense. Let's look at all the local extremas. This is a local maximum. What's the derivative here? This is a local minimum. What's the derivative? And this one. Okay. This is a local maximum. What's the derivative? Does not exist. Okay. So the proof of this theorem isn't very difficult, but I'll admit it now. We'll just kind of see why this tells us a little more than, or why is this more practical than the extreme value theorem. So let's see. First of all, the points at which the derivative is 0 and the points at which the derivative does not exist come up so often that they have a special name. So let's learn what that is, because I'm going to keep using it. If C is a point in the domain of F, okay, and either f prime of C equals 0 or f prime of C does not exist, we call C a critical number. those points at which the derivative is zero or does not exist within the interval are called critical numbers. These critical numbers come up a lot in our study of optimization problems. So I won't write this, but another way to say Fermat's theorem is to say, if f of c is a local extreme value, then c is a critical number. In other words, the only place that you need to look to find local extreme values are at the critical numbers. Okay? But here's a common misconception about critical numbers. Okay, if c is a critical number, it does not mean that f of c is a local extreme value. Okay? It's just a candidate. It may be a local extreme value. Okay? So, this is very closely related to the question I answered about velocity the other day. You know when we were talking about velocity, and we said, how do we know when the when the object changes direction? And we said, well, just make the derivative zero, make the velocity equal to zero, right? But that was not true. What did we have to do? The sign changes, right? So that's going to come up a little later, but that's kind of what this is. The point at which the derivative is zero is a critical number. It may end up being a local extreme value, but not necessarily. Let's practice finding critical numbers now, and then we can talk about Fermat's theorem a little more. So, consider this curve, y equals x cubed. Okay? Let's find the critical numbers. To find the critical numbers, we need to find y prime. Y prime is 3x squared. Okay? So, one thing we need to do is we need to find the values of x at which y prime is 0. And y prime is 0 when x is 0. So, that's a critical number. X equals 0 is a critical number. Then we have to find the values of x so that y prime doesn't exist. But y prime always exists, right? There is no function, there's no value of x at which this doesn't make sense. So the only critical number is 0. Okay? So in other words, if this function were to have a local max or local min, it would have to be at x equals 0. I don't have to look anywhere else. And if it doesn't end up being a local max or local min, then I can say with confidence that the function doesn't have any. Well, you all know what the graph of x cubed looks like. Okay? This is the graph of y equals x cubed. And of course there are no peaks or valleys there. And this is the point that we found as our critical number, but nothing special happening there. It's just that the derivative is 0. It's not a peak or valley. That's not why the derivative is 0. Okay? So this is an example of a function that has a critical number, but that the critical number never made it to become a local max or local min. And since this is the only place to look for local maxes or local mins, we can stop looking. We can say there are no local maxes. There are no local extrema. And then we don't have any endpoints to test because this is a function that's being defined on the whole real line. And so those were the other places to look for absolute extrema, right? Remember when we said we're either going to look at the endpoints or within the interval? Well, within the interval, there are no candidates and there are no endpoints. So we can say very confidently that there are no absolute extrema. There's no absolute min, there's no absolute max. Questions? Yes?
Is the only way of making sure that x equals 0 is not a local extrema by graphing it? Is that
For now, yeah. For now, we're just trying to say that that's this theorem, the converse of this theorem is not true, for Matt's theorem. Okay? Critical numbers don't translate into local extrema. Okay? We have to perform additional tests, and we'll do that in the next section. But it's fine. For our purposes, it's good enough. So now that we have these ideas formed, I promised you that I'm going to show you how to find absolute maxes and mins, and that's what we're going to do now. I'm going to show you a procedure for finding absolute extrema on a closed interval, of a function on a closed interval. Three steps. Okay? Then we can make sense of why this procedure is exhaustive enough to handle all the possible cases. Well, the argument I made earlier can now be formalized. At first, I will evaluate the function at the endpoints. Okay? Record the values. Then, I will evaluate the function at the critical numbers. And number 3, the largest in steps 1 and 2 give you the absolute max. And the smallest value in steps 1 and 2 gives you the absolute min. So let's justify that this procedure really works. Well, first of all, let's justify the existence of this procedure. This is a procedure for finding absolute extrema on a closed interval. Before you can justify the use of this procedure, you have to make sure that absolute extrema exist. Okay? Well, one of the conditions that the theorem requires is that you're working within a closed interval. So before you do any of this, you want to make sure that the function is continuous, right? Okay. So, but you can modify this procedure to handle the cases where the function is not continuous, and you'd have to treat those on a case-by-case basis. Well, we believe now that the absolute maxima is either at the endpoints or within it. So that's why we need this. But the question is, why do we evaluate the function at all the critical numbers? Why not just look at the local extreme values? Well, the answer to that is at this point we don't know how to find local extreme values. But we know that we know that those values will be one of the critical numbers. So, there's no way to know and to select those critical numbers that result in local extrema, so we're just going to do all the critical numbers. I know I made a big deal about not all critical numbers result in local maxima, but by doing this, we're not really losing anything. We're not assuming that any of these are local maxes and mins. But in the chance that they are, we're considering their values, because they may be the largest or smallest. Let's apply this procedure now to an example. Okay? Whose answer we already know. Okay? But without the graph, using just these three steps, we can find out where the local extrema or absolute extrema are. Okay, just to cover my bases here, I know that the function is continuous, and we're working within a closed interval, and so we know that what we're trying to find really exists. Okay, well, the first step is to evaluate the function at the endpoint. So, at the left endpoint, what's f of negative 1? 1, and at the right endpoint, the value is 4. In step 2, I need to find the function values at the critical numbers. Well, I have to find the critical numbers first. How do I do that? Find the derivative. And see where the derivative is 0 or the derivative is non-existent. Well, the critical numbers, x equals 0 because it makes the derivative 0. And that's it, because the derivative is never undefined. So that's the only critical number we have. Therefore, for step 2, I only need to evaluate the function at the critical number. F of 0 is 0. Okay. In step 3, I take the largest value. I have 0, 4, and 1. What is the largest value? 4. That's my absolute maximum. And between those three values again, what's the smallest? 0. So f of 0 equals 0 is the absolute minimum. Okay. This procedure is really that simple. Most of the work comes in for more complicated functions in trying to understand where the critical numbers are. Once you get the critical numbers, the rest is just evaluating the function at those numbers. Let's take one more example. So, h of x equals the cube root of x. So find the absolute extreme. H equals the cube root of x on this interval. Okay, negative 1, 8. Is this function continuous throughout the interval?
No. Yes.
Yeah.
There's an odd root, right? So we don't have problems with negatives. We don't have a denominator, so we're okay. Okay, step 1. H evaluated at the endpoints. That's the left endpoint. Cube root of negative 1 is 1. H of 8, cube root of 8 is 2. Okay. Step 2, find the derivative. Well, I can write this as x to the 1/3, then it might be easier to see that the derivative is 1/3 x to the minus 2/3. Okay? If I were to rewrite that, that's the cube root of x squared, the reciprocal of the cube root of x squared. Okay? Now, to find the critical numbers, I need to see when the derivative is 0. When is this 0?
Never.
No, okay. But that's not it. We also want to see where is this undefined. When x is 0, because that makes the denominator 0. X equals 0 is a critical number. Okay? Not because it makes the derivative 0, but because it makes the derivative undefined. Yes? So now, to complete step 2, evaluate the function at that critical number. H at 0 is 0. Therefore, you're comparing these three values. Okay? The smallest, absolute min, the largest, absolute max. Okay? And this, just a critical number. Okay? Alright. So that kind of tells us how to find absolute maxes and absolute mins. Okay? To study the other properties of functions, we need some more results about local extreme values. This is now section 4.2, and the title is the mean value theorem. And in parentheses, I'm going to say for derivatives. And in short, I'll just say MVT. Okay? The mean value theorem has a lot of consequences that are very useful. It's a very practical theorem. Not for its immediate results, but for the results that its consequences gives us. And before we can really understand what the mean value theorem says, we're going to take a special case and talk about Rolle's theorem. Rolle's theorem. Now, here's the idea. I'll write the hypothesis, and then we can think of the conclusion together. The hypothesis is that the function f is continuous on a closed interval AB, and that the function is differentiable on the open interval AB, so it's differentiable everywhere within AB. And the third condition is that the function value at A equals the function value at B. Okay? And equals 0. Although that the function values equal 0 is not necessary. It's enough to say that f of A equals f of B. But for simplicity, we'll just say that they're equal and they're equal to 0. Then, the conclusion that Rolle draws from these three criteria is actually very intuitive. We'll reserve this space to write the conclusion, but I'd like you all now to draw a function that satisfies these criteria. So in other words, you have 2 points A, B on the x-axis, and I'd like you to draw a curve that's continuous and it's smooth enough, so it's differentiable. Okay? And it's differentiable everywhere in the interval. And what do you notice? You're forced to have a peak or valley, yes? Does that make sense? Okay, the boring function you can draw that connects A and B is this function that's constant. that's perfectly, that's continuous, that's differentiable, f of a equal f of b equals 0, that's fine. That's pretty boring. Although the conclusion of the theorem handles that possibility as well. But instead, let's say that it's not a constant function. You notice that you have to have, whatever you do, you have to have at least one peak or valley. Yes? And because of the differentiability condition, that peak has to be a smooth peak. Can't be a cusp. Can't be like that, because it's got to be differential. Okay? So, but what can you say about a smooth peak in terms of its derivative? The derivative is 0. So that's what Gross said. That if these conditions hold, then the function has to have a point at which the derivative is 0. There's no other way. Okay? But that point, at least once, where f prime of c equals 0, so that it has a 0 slope there. So the conclusion now from these three criteria are that then there is a point, there is a number, c, okay, that lives within A and B. There's a number c within A and B. Okay, such that the derivative is 0. Okay? Now, even if your curve is not as simple as this, perhaps you may want to join these 2 points by a curve that's slightly more complicated, like this, in which case you'd have two points at which the derivative is 0. Okay? But Rolle's theorem guarantees that there's at least one. If you have 2, it does not invalidate the theorem. Okay? There's at least one value where the derivative equals 0. Okay? So, I'm just going to write the word proof. Okay? And I'm going to talk through it. I'm not going to write anything. And maybe it'll be homework questions right to proof. It's actually very simple. We're going to start by the very boring case. Okay? We're going to start by thinking of the simplest function that satisfies these three criteria and try to argue our way into the conclusion that this conclusion is inevitable. And the simplest possible case was the first picture I drew. A straight constant function that connects A and B. Right? That's one possibility. And if that's what your function looks like, then the derivative is 0 everywhere. Right? So at least there is a point where the derivative is 0. So that case is handled. Yes? Okay.
What?
So let me draw a picture. Case 1, your function is constant. So here's your function. If your function is constant, then the derivative is 0 everywhere. Remember that the derivative of a constant is 0? Right? So then there is a point at which the derivative, at any point here, has a 0 derivative, 0 slope.
Where's the max or the min?
There's nothing said here about max or min. There's only something said about there being a point at where the derivative is 0.
Just thinking ahead.
Yeah. So we're just trying to verify this theorem here. So the first case is the case at which when the function is constant, then it's very easy to see why this conclusion is true. Now, for case 2, it's not constant. Yes? In other words, if the function is not constant, then at least at one point within A and B, the function value has to be different than 0. It has to be either above or below. So let's say it's above. Okay? That existence of that point already tells us that the function is not continuous. But then that means that we have to have a continuous curve. So anyway, even if I take the point here, we know that in order to come back to hit 0, right, we're going to have some properties here. Part of this hypothesis guarantees the existence of extrema. Which part?
F of A is equal to
No, this one. This is the condition for the extreme value theorem. If you just know that, you know there's absolute extremum, right? Does that make sense? Okay. Now, if the function is not constant, yes, then it's going to have a maximum that's different than it's going to be more than 0. Yes? Okay. Well, if your absolute max is not at the endpoints, then where is it? It's at a local max, right? Okay. And where do local maxes occur, according to Fermat's theorem? At critical numbers, right? And what are critical numbers? When f prime exists, isn't it 0 or it doesn't exist? Well, f prime always exists in this setup because of condition 2. Okay? So going back here, where does the function have an absolute max? At a local max, and that happens when the derivative is 0, right? Because of Fermat's theorem. That's the key, the derivative is 0. So we found a point at which the derivative is 0. And that's the conclusion of the theorem. So that's what you argue. The proof is based on Fermat's theorem. Okay? And that's all I'll say about Rolle's theorem. So, okay, let's look at this question again and start over. So we want to show that this equation has exactly one real solution. Okay, now there are two things that we actually have to show. Okay, we can break down this question into two parts. We want to show that the equation has a solution. Okay, and that two, that this solution is unique. Okay, that there are no others. There are no other solutions. Okay, that's exactly what it says. Exactly one real solution, that it has the real solution, and that's the only one. Now, we've solved this type of problem before, where we show that an equation has a solution, and we use IDT to do that, the intermediate value theorem. And I'll show you how again. And to show that the solution is unique, we're going to use Rolle's theorem. And it's a very nice proof because it uses an indirect approach, proof by contradiction, which is always fun. Okay, so that it has a real solution. We're going to start by saying, suppose the left-hand side was our function x cubed plus 3x plus 1. So what we'd like to do is show that f of x, or f of c equals 0 for some value of c. That f of c equals 0 for some value of c. Now, we know that that could be argued to be true if 0 is an intermediate value of the function. In other words, if we can come up with an interval so that 0 is between f of a and f of b, we want to come up with a and b, we want to come up with an interval to do that. Well, consider an interval -1, 1. Okay? Let's see if it'll work. F of -1 is -1, or -2, actually. Right? just said it's negative. And f of 1 is positive. Okay, 5. Okay, so the point is, if we're talking about this function, we know that it's continuous on this closed interval, and we know that 0 is an intermediate value. Okay? So, if we were to draw a picture, here's negative 1, here's 1. We know that these 2 points are on the graph. And that it's continuous, so as we connect these 2 points, we have to hit the x-axis somewhere. And where we hit it, that's the solution of the equation, because that's where this quantity becomes 0, which solves the equation. Yes? Okay. So, since f is continuous on negative 1, 1, and 0 is an intermediate value, okay, we can say that the intermediate value theorem guarantees a number c within the interval, so that f of c is 0. Okay? Does that make sense? Any questions about this part? Okay. So we're done with the first step, that we have a solution. Now we have to show that that's the only solution. And here's what we're going to do. Okay? Aiming at a contradiction. Okay? Suppose there's another solution. In other words, suppose there's another number d, okay, at which the function takes on the value 0 again, or some d. That's not equal to c. Okay? Alright? This is exactly the opposite of what we want to show. That there is no other number for which f of that number equals 0. So, aiming at a contradiction, we'd like to suppose that we have such a number, and we're going to get a contradiction now. Okay? For the purposes of our proof, okay, we can suppose that this number d is more than c. So, and the proof works if it's the other way around as well. So in other words, I have a number c. I know for a fact that the function goes through that point. Let's say I have a number d that's bigger than it, at which the function is 0 again. Well, what conclusion can you draw if that were the case?
There's a number c that goes between both of them.
Okay, but there's a number c between these two. That, well, we can't call it c. It's called f. Terrible name. F is the name of the function. Let's call it alpha. Between c and d, that what? That the derivative at that point is 0, right? Who tells us that that's true? Uncle Roll, right? So, but let's make sure that we have our bases covered. We have to explicitly show that all the 3 conditions are satisfied if we were to argue that way. Well, the first condition has to be that f is continuous on a closed interval. Well, the function is continuous everywhere, so that condition is fine. The second is that the function has to be differentiable within c and d, right? Okay, well, what is f prime? Does this function make sense everywhere? So in particular, between c and d, it makes sense. Great, so the second condition is satisfied for Rolle's theorem. What's the third condition? Exactly. Well, in this case, we're working with the integral CD. So f of c equals f of d equals 0. That's true. Right? Great. So the three conditions are satisfied. So then we can say by Rolle's theorem, okay, f prime of alpha equals 0. Okay, for some alpha within the interval CD. So there's a point at which the derivative is 0. So if this were our picture for our function, then we have to find there should be a point where the derivative is 0. Yes?
Mm-hmm.
Okay. But remember, we're supposed to get a contradiction. Okay? And here's where the contradiction comes in. Let's write it here. Saying that f prime of alpha equals 0 is like saying, here's f prime, it's like saying 3 alpha squared plus 3 alpha equals 0, right? No, not even 3 alpha, just 3. This is what it means. This is what Rolle's theorem guarantees, and Rolle's theorem is true. That's a contradiction. Do you see why?
It's your square root in a zero.
Yeah, well, there's no number where it's squared plus 1 is 0. Okay? Now, we're looking for real solutions here, okay? And calculus is being done with real numbers. So, there is no, this doesn't have a solution. This is our contradiction right here. The existence of this type of alpha is a contradiction. This alpha can't exist. This equation can't have a solution. F prime can never be 0. Okay? So then, what is our conclusion? We'll trace back where that came from. Where did the problem start? The problem started right here. Suppose that f has another solution besides c. And so our conclusion is that there is no other solution. Besides C. Therefore, the solution that the intermediate value theorem guarantees is unique. Okay? This is a good problem because it uses two theorems and it introduces you to a very popular proof approach, which is by contradiction. Okay? Okay. The star of the show today is the mean value theorem, and we have to reserve enough time to talk about that. So, and we're going to try to come up with this theorem again ourselves. We're drawing some pictures. So here's the statement of the mean value theorem. That f is continuous on a closed interval AB, and that f is differentiable on the open interval AB. Okay, and then we want to make some conclusion about derivatives, about slopes. So the setup for the mean value theorem is very similar to that of the Rolle theorem, but the last condition is not necessary. Okay, in other words, if we were to draw a picture that satisfies these two conditions, it's not necessary that f of A equal f of B. Okay? So we'll just draw a curve that connects these two, making sure it's continuous and differentiable, so it's smooth enough. And here's a visual of what this theorem says. Connect the 2 points. In other words, draw the secant line from A to B. Okay? That's the secant line. From f of A f of A, and B, f of B. Alright? Now, try to imagine this, that you have this line, moving in this direction until it becomes tangent to the curve. Okay? Until it becomes tangent to the curve. So that's why I brought this box. I hope it actually serves a purpose here. Let's see if we can do this. So,
He doesn't need to see it, he just needs to see it.
and there's something special about that tangent line over there. So if you just move this in the direction of the arrows that I pointed out, okay, and then until that line becomes a tangent, right? Tangent lines have very intimate relationships with derivatives. What is so special about the slope of that tangent line? It's equal to the slope of the secant line, right? Does that make sense?
Yes.
Okay. So we could kind of intuitively at least believe that every time we have this type of setup, we can find a point C between A and B at which the slope of the curve at that point is equal to the slope of the secant line that connects the endpoints of the curve. Okay? So that's actually the conclusion of the mean value theorem. That the slope of the tangent line at C is equal to the slope of the secant line. Now let's generate an expression that gives us the slope of the secant line. Right? So this would be f of b. This would be f of a. So the slope is the change in y, which is f of b minus f of a over b minus a. This is actually the conclusion of the mean value theorem. And these are the conditions that have to be satisfied for this conclusion to be inevitable. And this is the picture. Okay. Now, we'll talk about the proof of the mean value theorem just a little bit. Just a little bit, okay? And you can fill in the details at home for homework. But here's the idea. The idea is simplify the problem. So that when you create a new function, satisfying Rolle's theorem. That's the approach for proving the mean value theorem. Okay? You're working with a function f, and using that function, create another function that satisfies Rolle's theorem, and then use Rolle's theorem to conclude the result. So here's the idea. We're going to come up with an equation for this line. Okay? We have the slope, it's f of b minus f of a over b minus a, and we have a point. Here's the point. So with a point slope formula, we can write down the slope or the function. So let's call that function g. Right? G would be, or maybe g minus the y value, this point, it's f of a, right? Equals the slope, is f of b minus f of a over b minus a, times x minus the x coordinate at that point. What's the x coordinate?
8.
8. And then if we solve for g of x, then we have a new function that represents the blue line. So then g of x is f of b minus f of a And now we're ready to create the function that we want, which is a function that satisfies Rolle's theorem. And it's going to be a combination of f and g. Okay? So we're going to call this new function h. And it's going to be f minus g. Okay? So visually what's happening is, on the picture, at this point, if you do f minus g, what will be the result? Well, f and g have the same y value, so if you subtract them, what do you get? 0. So your function h will have a value of 0 at a. And similarly here, if you subtract the two function values, they're equal, so your function value at b would be 0. Alright? But then f and g are each continuous and differentiable, so their difference will be continuous and differentiable. But in addition to being continuous and differentiable on the appropriate intervals, you'll have the endpoint values being the same. And so you can use Rolle's theorem on h. H satisfies the conditions, the three conditions of Rolle's theorem. Okay? And what does Rolle's theorem tell us? H satisfies, so what does Rolle's theorem tell us? What's the conclusion?
Function f is continuous.
It tells us that h prime of c equals 0 for some value of c. Within a and b. Right? Okay, let's write it down. Is h continuous on a b? F is continuous, g is continuous, the difference is continuous. Yes? Okay. Is h differentiable on a open interval? Yes, for the same reasons. F and g are each differentiable. Okay. Furthermore, is h of a equal to h of b? H of a is f of a minus g of a. Yes? At a they have the same value, so their difference is 0. Similarly at b. Therefore, h satisfies Rolle's theorem. Therefore, we can write down the conclusion, which is that the derivative of h at some point is equal to 0. Right? Looking here, what's the derivative of h? F prime minus g prime, right? So just rewrite h prime of c equals 0. So f prime of c minus g prime of c equals 0. Yes? In other words, that f prime of c is equal to g prime of c. Yes? Look at g. This is g. This is g is mx plus b. Yes, something like that. What's the derivative of g? G is a straight line. So the derivative is it's constant. What's that constant? Okay, we were getting somewhere. You just had to kill it, right? All right. If I just pointed at this line and I said, what's the derivative of the slope of this function? What would you say? It's a slope, yes? The slope 0? No, so why would you say slope is 0 for g? I tried to do color coordination. See? Blue line, g, you know. What's the derivative of g? Thank you. This is the derivative of g, right? The slope. This was the slope. Remember when we wrote the function? So, equals, so in other words, f prime of c equals f of b minus f of a over b minus a. And then, this is the easiest part. No, it is funny because we're done. There's nothing else, right? That's what we have to prove. If you're at all awake, yes? This is what we're getting to. Yes? Raise your hand if you're awake. Thank you. We're done. That's all. You just draw a little square shaded. Okay?
QED.
Okay, the consequences, I promise that the consequences of this mean value theorem are very important. Before getting into the purely mathematical consequences, I want to give you a physical interpretation of what the mean value theorem says. So if we talk about so S equal F of t as a position, of an object moving in a straight line and moving along the straight line at time t. Okay, and we are interested in our time interval being from 0 to 4. Okay, and we're going to suppose that the position at 0 is equal to 0, and that the position at 4 is equal to 160. Okay? So let's put some units here. We're talking with meters, and we're talking with seconds. Let's see what the mean value theorem says about this motion. So we have, the mean value theorem says, in assuming that this function f is differentiable and continuous on the appropriate intervals, it says that there is a time, okay, let's call it, let's not call it t, let's call it c. There is some time between 0 and 4 seconds so that S prime at that point is equal to what? S of 4 minus S of 0 over 4 minus 0. Let's work that out. S prime of C equals
160 minus 0.
160 minus 0 over 4, so 40 meters per second. This expression on the right-hand side represents what? In this context. In this context, in context of motion. Change in position divided by change in time. Velocity. Okay. So, and we're talking about the velocity over an interval, right? So this number is the average velocity over the time interval 0 to 4, right?
At some point.
And this, the derivative of position represents what? Instantaneous velocity. Okay? So let's write that down. So the mean value theorem tells us that there is a moment
Between 0 and 4 seconds.
at which the instantaneous velocity equals the average velocity. Okay? Perhaps these numbers didn't make the point clear. Let me do one more example. Suppose it takes you 2 hours to go 100 miles. Yes? Okay. What is your average speed? 50 miles per hour, yes? Now, that doesn't tell you that the speedometer always shows 50 miles per hour, right?
Mhm.
But if your average is 50 miles per hour, then you must have some speeds that went over it and some speeds that went less than 50 miles per hour. What the mean value theorem is saying, that your speedometer at some time within your 2-hour trip must have been exactly at 50 miles an hour. Does that make sense? So that's the interpretation of, well, a physical interpretation of what the mean value theorem tells us. So, in summary, here's another way to look at the mean value theorem. Before we talk about some other mathematical consequences. So, MVT nutshell version. Okay, very simple. That slope of tangent, okay, equals slope of secant at some point. That the instantaneous velocity equals average velocity. And now, since we're talking about rates of change, we don't have to only stick to physical applications. We could say instantaneous rate of change equals average rate of change. Okay. If the population was 5, and then the population was, after 2 days, of 500, right? Then the average increase in population is 49.5 per day, or whatever, if I did my math. But it's just saying that at some point, the instantaneous rate of change of population is equal to the average rate of change of population. Okay? At some point. F prime of C equals f of b minus f of a over b minus a. Okay? It would help if you could make the connection between this statement and one of these interpretations when you're thinking about the mean value theorem. All right? Okay. So a corollary is like a theorem, but it's a consequence of a larger theorem. Okay? So this is a corollary to the mean value theorem because it comes from that. Okay? So you can just think of it as a little theorem. Corollary: if f prime of x is equal to 0 for all x in an interval, then f of x is constant on that interval. Okay. The proof of this is a very nice application to the, of the mean value theorem. Very simple. Okay. The condition: f prime is 0 everywhere in an interval. The conclusion: that the function is constant everywhere in that interval. Okay. Now, how could you argue that the function is constant everywhere in that interval? There are too many points in the interval, so we want to simplify our approach. We can't possibly find every single value. But instead, we could say, if we pick any 2 points in the interval, any 2 points, okay, and the function values are forced to be equal, yeah, right?
Mhm.
Then the function values have to be the same everywhere, because those 2 points were arbitrary. They were any 2 points, right? So since you could do that with these 2 points, you can do that with these 2 points and any 2 points, and they're all the same. And so the function values have to be the same everywhere. That's the idea. Okay? So to prove, we can say let x1 be more than x2 be any 2 points in the interval. The interval that the corollary mentions, the interval in which the derivative is zero everywhere. Well, according to the mean value theorem, and I have to pause here for a minute and make sure that my function satisfies the conditions of the mean value theorem. Well, since we're talking about the derivative being zero everywhere, means the derivative exists everywhere, right?
Okay.
Okay? And if the function is differentiable, then it's continuous. Yes? Okay. So we can say according to the mean value theorem, and then write the conclusion of the mean value theorem. That there exists a number C. I'm going to go back and just for stylistic reasons, make x1 less than x2. Doesn't really matter. Okay? There exists a number C within x1 and x2 so that the derivative at C equals the average rate of change. The average rate of change of the function in this interval is what?
Equals x to minus f of x1.
Okay. And by the way, the reason I'm saying x1 less than x2, just to point out that they're different numbers, right? I don't want to come to this conclusion, okay, and then worry about that x1 and x2 were the same number, and I haven't shown anything, right? I just say f of 2 equals f of 2. But you want to make sure that these two are different numbers. That's what we want to get to. Well, let's multiply both sides by x2 minus x1. Yes?
Yes.
Yes.
What do you know about f prime of c? What is the value of this f prime of c? Why?
Because
According to the hypothesis of the theorem, f prime is zero everywhere. So in particular, f prime of c is zero. Yes? Okay, so we know that this is equal to zero. That means the difference between f of x2 and f of x1 is zero. If the difference of two numbers is zero, then they're both the same number. So then, therefore, f of x2 equals f of x1. And since this was true for any two numbers, it's true for all the numbers within the interval. Okay? Therefore, the function is constant everywhere. Any questions about the argument there? Before I talk about the next two theorem, or the next corollary, I want you to answer this question. It's very easy. Write two functions whose derivative are both x. write two functions so that the derivatives of each of them is 2x. The derivative of what function is 2x? X squared. The derivative of x squared is 2x. So one of the functions is x squared. Now give me another function whose derivative is 2x.
X to the power of 4
X to the 4,
over 2.
okay?
No.
The derivative of that would be
No, over 2.
x cubed, right?
Oh.
You want the derivative to be 2x. I told you that the answer was easy.
X squared.
2 squared plus 1. Thank you. X squared plus 1. The derivative of x squared plus 1, the derivative of x squared is 2x, derivative of 1 is 0, right? So there, we got two functions, different functions that have the same derivative. What can you say about these functions? Are they similar? How are they different?
Shifted up 1 unit.
Shifted up 1 unit. Okay, so algebraically, how are they different? Plus 1. But I could have easily said plus 2 and nothing would change. Or I could say minus 5 and nothing would change, right? So in general, how would you generalize that? Plus C, plus some constant. So this next corollary just, states that fact, that if two functions have the same derivative, then their difference must be just that one has a constant. Their difference is a constant. Okay? Does that make sense? If f prime of x equals g prime of x for all x in an interval, then f of x and g of x differ by a constant. Yes? Okay. Now we kind of understand why because of that example over there, but we're still gonna write a formal proof because it's really simple. And these types of proofs are good because they build on what we just saw. This is going to be based on the other corollary. What was the other corollary? That if the derivative is always 0, then the function is constant, right? So now you have this idea. Build a function whose derivative is always 0. Isn't this always 0? According to the hypothesis? So build a function that has, right? So you want to build a function. So you come up and you say you build a function. This is a nice function to build. Let h be this. So that h of x, h prime of x, which is the difference in derivatives, is 0. Right? Does that make sense? So now just think about h. If h prime is 0, then what can you say about h? H of x equals constant, right? According to the previous corollary. Now rewrite this equation, but instead of h, write down what h represents. And then? And then? That's it, thank you very much. Right? that f and g differ by a constant, yes? And that's what we're doing. We're deferring f and g by a constant.
That's what
Yes.
it's doing.
You're just playing, right? I mean, you knew that was okay.
Chico Pirates.
Was that the second one?
Yeah, this is the second corollary. Now, this example is describe the functions whose derivatives are 2x. Same question as I had before. But I don't want two functions. I want to describe all the functions whose derivatives are 2x.
X squared plus c.
Differ by c.
Right? X squared is one of them, the simplest one perhaps. And then, since all other functions that I want have this derivative, then the only difference between x squared and all the other functions should be a constant. The difference between f and x squared should be a constant. And so, f of x equal x squared plus c describes all the functions whose derivatives are all 2x. And the picture for all these functions is congruent parabolas that are just shifted vertically. Okay? So, well, c can be plus or minus, so we don't have to write plus or minus c. There's nothing that says c is a positive constant, just that it is constant. So you could have plus negative 4, for example. Right? So, if we were to describe the graph of these, we'd say there are parabolas whose vertices lie on the y-axis and whose focal point has, or focal distance is the same. Right? Then I would kind of set up everything. But you know, this picture says a lot, and families of functions. Okay, this is a family, or a family, not family, a family of functions, and this is a family of curves. Okay? Now, let's do a real world example here. So an object is dropped. From a height of 300 meters. Okay. Find its position. Or find its position. Yeah, find its position and velocity. After 2 seconds. Okay. This is a direct application of this family of functions business, direct application of the corollary. So ultimately, the mean value theorem allows us to answer this question. Okay, well this is being done on Earth, and the acceleration is only due to gravity. And the acceleration is known to be negative 9.8 meters per second squared. So for our motion, we're assuming downwards is negative, and acceleration pulls us downwards. Okay? The initial height of the object is 300 meters. Now, A is a function of time. As time goes on, the acceleration is 9.8. But it's a special function. What type of function is it?
Acceleration.
It's a constant function, right? Acceleration is just 9.8. Now, we know that acceleration is closely related to velocity. Yes? And that velocity is closely related to position. And that's ultimately where we'd like to go. Yes? So instead of writing A equals negative 9.8, we can say that B prime equals negative 9.8. And let's see if we can find V from there. In other words, I'm asking the same question as I did over there. I want to describe all the functions V whose derivative is negative 9.8. And the simplest one is what? Negative 9.8t. And to describe all of them, plus t. Does that make sense?
Yes.
Great. So now, but this is a particular problem. We don't want to describe the motion of all the objects that were dropped. We want to describe all the objects that were dropped from 300 meters specifically. Yes? And so, but in general, not only are we interested in objects falling, but objects that were dropped, not thrown down. There's a difference between throwing something down and dropping it. What's the difference? I'm sorry? Different acceleration? Well, no, the acceleration is only due to gravity. If you throw it down, it just starts faster. If you just drop it, what's the original velocity? Zero. In other words, since you dropped it, instead of throwing it, your velocity at time 0, which is when your experiment begins, is equal to 0. Now this is what velocity is. What's the velocity at 0? C. Right? You plug in 0, so you get 0 equals C. So C equals 0. This tells you that C equals 0. So then, the velocity is equal to negative 9.8 t plus 0. Okay? This gives us all the family of curves, but we want the one that describes our experiment. Okay? So let's answer the first part of this question. We want the second part. Find its position and velocity after 2 seconds. So velocity after 2 seconds is very easy. The velocity after 2 seconds is twice that, 19.6 meters per second. Okay? Anyhow, we wanna find its position. V equals negative 9.8 t is the same as saying S prime equals negative 9.8 t. And so now, if I'm asking for the position function s, I'm looking for a function whose derivative is this. So let's think about that for a moment. Very good. Negative 4.9 t squared plus c. So we take care of all the possible functions. Right? So if you just do the power rule now, and you check the derivative, you see that you get negative 9.8 t. Okay? Okay, and we want to be more specific so that we're modeling this. We want to find out what this value of c is.
Does that refer to C equals 0?
No.
That's
We know what the position is. Okay, C, this c is a different c than this. So maybe I should say k.
C2 or
Or C2. There's a different c. It's just another constant. So, but S has to satisfy that condition that it was dropped from a height of 300 meters. So at the beginning of the experiment, when time is 0, the position is 300. When time is 0 means this quantity is 0, this is 300. So what is K? 300. So, you know, to preserve space here, I'm just going to say K is 300. Is that clear? Okay, and then now find the position after 2 seconds, plug in 2 here, and you have your result. And that'll be the position after 2 seconds. Okay. And this was the motivation for Isaac Newton to invent calculus. If we know how to begin, can we predict where we're going to go based on the laws of nature? Okay. So, and the only law of nature that we have used here is something very simple: is that gravitational force is constant, nearly constant on the surface of the Earth. So, based on that and based on the tools of calculus, we can predict where we're going to be after 2 seconds or after any amount of time. Okay. So, you know, the mean value theorem is pretty powerful. Okay. Now I'm going to do a more mathematical application of the mean value theorem. So prove that absolute value of sine A minus sine B is less or equal to the absolute value of A minus B. Okay, so we're going to have to, this sine A minus sine B looks like a f of b minus f of a situation. Well, nothing would change if I replace this by b and this by a, because we're working with absolute values. So maybe it's easier to the eye if we write it this way. Nothing really changes. Yes? Okay. So since this is looking like an f of b minus f of a situation, naturally, if you listen to the problem, it tells you define a function f called sine x. Yeah? And then see what interval you want to work with. How about AB? Yeah? Okay. And then let's try to create some of these expressions in a meaningful way. So this is like f of b minus f of a, and this is b minus a, right? The quotient of these two, the mean value theorem says something about, right? The quotient of those two. So let's see what the mean value theorem says. It'll naturally lead us somewhere. It says that f prime of c equals f of b minus f of a over b minus a. Yes? Okay. What's f prime of x? Cosine x. So cosine c is equal to f of b, which is sine b minus sine a over b minus a. Okay. So we're getting close. One of the things that we need is these bars, these absolute value bars. So we'll just put them. Because we know that if two quantities are equal, then their absolute values are equal. So in other words, absolute value of cosine c is absolute value of the right-hand side. Okay? And there's nothing lost if I just say cosine c equals absolute value of the numerator minus the absolute value of the denominator, or divided by the absolute value of the denominator. Okay, we have to get an inequality now, because the result that we want to show is not inequality, it's an inequality. Well, whenever you have absolute value with sines and cosines, it's really simple what the inequality is. Cosine is always less than what? 1, right?
Yes.
So I can come here and I can say that cosine is always less than 1. Do you agree? So, in other words, if I just flip this around, then I'm saying that sine b minus sine over b minus a is less or equal to 1. Does that make sense? Now, with absolute values here, now multiply both sides by b minus a, and you're good.
Multiply both sides by 2 minus. So equals b minus a.
Yes?
Mm-hmm.
The absolute value really simplifies things, because when you have an inequality, you want to make sure you're multiplying both sides by a positive number. Right, so it actually simplifies it. But this would be supremely difficult without the mean value theorem. Although sine and cosine are just geometric ideas, this basic property is to show without calculus. Okay. Any questions?